Welcome to Dr. Jimmy's Applied Calculus, Section 3.5, Limits at Infinity. So, I could ask, what happens to f of x as x gets larger and larger or grows without bound? So instead of x approaching some value, we let x get bigger and bigger. Then what happens to the heights, or the f of x, the expression? So we can write that as the limit as x, well, we could write it approaches infinity, but that would mean x becoming larger and larger without bound of the expression f of x. That will be our notation. So we can make sense out of that. As x gets larger, does f of x tend to become something? And we could ask that if x grows without bound, but we have large negative numbers, what happens? So x approaching infinity or minus infinity, that terminology would mean x growing without bound, either positive or negative. So, to compute some of these types of limits, we could invoke what I brought up in an earlier section about the properties, the conceptual properties of infinities and division by zero. So we could look at something like the limit as x goes to infinity of 4 over x cubed. And so we would write by evaluation 4 over infinity cubed. Sorry. Or 4 over infinity cubed is essentially just large, again, infinity. And the reciprocal of infinity, we found out, was a 0. So we get that limit. We could also reason this out. As x gets very large, these are reciprocals of large numbers times 4, which would be very small or getting close to 0. Or something like 3x squared. If we substitute infinities, 3 infinity squared, well, infinity squared is infinity, 3 of those is still infinity. Or something of the form minus 3x minus 2 would be minus 3 infinities minus 2, which would come out to still very large negative. So many of these things we can go back to and recall this sort of conceptual arithmetic using infinities. So now we may keep working with other expressions, and we found out that some forms of these arithmetic with infinities are indeterminate. So we'll bring up rule concerning polynomials. So if we have a polynomial and we look at the limit becoming infinite, either plus or minus, I'll just put the plus here, that limit is the same as the limit of the leading term. So no matter how many terms we have in the polynomial, limits at infinity, plus or minus, we could replace that expression just by the leading term, the term with the highest power. So that means there are certain things we could work out that might not have worked out so well from my arithmetic on infinities, because if I did that in this case, evaluation would have done 3x squared would have given an infinity, minus 7 large is minus large, and so we would have come to this indeterminate form. So the negative opposite signs in this progression mean that we can't just come up with the correct thing looking at this. But now, what we know is that it does whatever happens as the x grows without bound is determined by this leading term, the highest power, in this case x squared. Of course, that becomes infinite then. But other things like 3x cubed plus 2x minus 7, all divided by 2x minus 8 plus 4x cubed minus x squared. The polynomial expressions I'm allowed to replace by just the leading term. So 3x squared plus 2x minus 7 I can replace by 3x cubed. 2x minus 8 plus 4x cubed minus x squared I can replace by its leading term being 4x cubed. So wherever, if I have limits at infinity, which is important, this only works for limits at infinity, with a plus or minus infinity. I can just use leading terms in polynomials. And so in this case, once I have 3x cubed over 4x cubed, that's easy to reduce to 3/4, and so the limit is 3/4, a nice number. Another example, limit x at infinity, 5x squared plus 2x minus 7, all divided by 3x cubed plus 8x plus 4. So, limit at infinity, I can then just use these leading terms. So in the numerator, square is the greatest, in the denominator, the cube is the greatest. So I have 5x squared over 3x cubed. And then if I take that expression, I can divide out some x squared and end up with 5 over 3x. Or now, if I evaluate with infinities, 5 over 3 infinity is actually a 0. Or I have the limit as x approaches infinity, 5x cubed plus 2x squared minus 6 over 3x minus 2x squared plus 8. Limit at infinity, I'm allowed then to make this 5x cubed divided by the lower leading term would be minus 2x squared. So 5x over minus 2. So x becomes infinite, but we have a minus, so minus infinity is the case now. So limits at infinity, different than limits approaching a number when we deal with polynomials. So limits at infinity, we just need the leading terms. For the previous types of limits, that wasn't true, so you have to keep that straight. Limits at infinity, the plus or minus infinity. We can drop all lower terms and keep the highest terms in polynomials. So now, if we take limits at infinities and how that relates to the graph of a function, let's consider y equal 3x squared plus 2x minus 1 over 2x squared minus 5. And this may have many characteristics, but if we look at the limit as x approaches infinity of this y, we get 3 halves. We can go back to that, but it would be 3x squared over 2x squared reduced to 3 halves. And the limit as we approach minus infinity of this same expression, we would do the same thing and it would reduce to 3 halves. So if we look at the horizontal line, y equal 3 halves, these limits at infinity are telling us that as x grows without bound, the function graph looks more and more like this straight line. So as it exits this particular graph, we would see this behavior of approaching this line. And the limit as x becomes very large negative has this property, so we would see it approach that same y equal 3 halves. So near the edges of the graph we see this asymptotic behavior. So y equal 3 halves is an asymptote if the limit at infinity happens to be that number. And so, but this is a horizontal asymptote. Limits at infinity, if those are numbers, get horizontal asymptotes. But other things like 3x squared minus 2x plus 8, the limit as x becomes infinite or approaches infinity, limit at infinity, is the leading term, which would go to infinity. And the limit as x approaches minus infinity is the limit of the leading term. And so we take large numbers, negative, and square them, we end up at positive, so this whole thing is positive and very large, so infinity. So graphically, this is giving this characteristic as it leaves, it's just going up positive forever on both ends here. So if the limit was minus infinity, it would go down forever. So we're either going to get a constant number and we get a horizontal asymptote, or we get an infinity and we get this up or down forever behavior near the edges. And no asymptote here.